All right, we're back. Now, what I had you do in the meantime was watch a video I did the other day from Back in the Closet with convection to see how it works as kind of a flow. So the rules are convection only takes place in fluids. And what that means is gases or liquids. Can't work in a solid. If you took a log and heated one side of it, the log isn't incapable of like flowing. It's rigid, right? It can only happen in things that flow, and that's what fluids are. Because it's less dense, and going back to the beginning of the year with density and heat, warm air rises and cool air sinks. And what that does is creates these currents called convection cells, cells. Um, so, like an example that I always do, we'll do some drawing here. I don't know how well you can copy this, but give it a go. So let's say that this is a shower. All right, there's the tub. The shower is like coming out of the wall here. The curtain rod is coming straight at us, so there's the curtain rod and the shower curtain. Maybe you have two on each side of the thing, right? So you turn on the shower, and it's a hot shower. So where it's hot, you're going to make this air less dense. That air is going to rise and rise and rise, but it can't really go too far because the ceiling's there and the wall's there. So it spreads across the ceiling over here to where, in a relative sense, it's cooler. Which means that the air is going to sink and sink and sink. Now, what can happen in your bathroom if you've got curtains? If you've ever noticed this, is that sometimes the curtain like blows back at you. It's because you're creating a convection cell in your bathroom. If you have the fan off and the windows closed and the door closed and all this, you can get this thing moving. Now you can see examples of this all over the place. You can put a pot of water on a stove, and when you're making your mac and cheese, and you'll see the noodles like whipping around in little convection cells. Um, if you have a fish tank with a heater, it's hot on one side, and then the water kind of flows around. It's a big thing. Earth science tests like this. If we talk about the beach, and we go back to the lab that was sand and water, remember that sand heats quickly. Let's make the water blue. That's just what the lake looks like. And here's the water, and we're at Lake Ontario. We're at the ocean. Since sand heats a lot faster than water during the day, and if you've gone to the beach in bare feet, you recognize that it's hot, and then you run to the water to be cool because water heats so much more slowly. Well, where it's hot, the air is going to rise. Where it's cool, the air is going to sink, and we get a convection cell locally on shorelines. Now, if there's a major weather pattern in town, that's going to blow this thing right out. Like this is smaller scale. Well, let's say it's a reasonably still day. You can get this happening at nights. I'm sorry, during the day, because it's because of that differential heating of land and water. What would happen at nights? Well, at nights, if you remember, sand cooled down more, water doesn't cool down as easily. So this whole entire thing reverses, and you can get a breeze blowing offshore at night. Again, if no other major weather patterns are coming through, interrupting you. All right, so how hard do I want to hit these? Not super hard. But let's just do let's do a quick and dirty version of what are the things that can happen to this energy as it's coming at us. This insolation, incoming solar radiation. Well, it interacts with our surface in a bunch of different ways. Some of these, like you might just kind of don't overthink it, like reflection. Oh, you've used a mirror. You know what reflection is. Hits and bounces back off, right? So some energy comes at us, bounces right back into space like a mirror. Tops of clouds are infamous for this. The poles that are covered in ice, since ice is white, are pretty good at reflecting energy right back off. Some gets bent. I'm going to even spell it right. Refraction. Um, and I don't know if I have the example of the straw in here. Those are the other notes. But if you put a straw into water, I don't want to put a pen into my coffee for real. But if I put that marker in there and you can see through it, you ever see this thing where like it looks like it's bent? It's not actually bending. The speed of the waves is changing, and the light waves themselves are bending. Energy bounces off like air molecules like a disco ball. This is scattering. I'll do one quick thing with that below. Or what is really kind of the critical part, absorption, if it gets taken in by an object, warming it up like a hot road. All right, so some energy bounces right off of our atmosphere, some right off of like clouds or ice. What makes it all the way to the surface? Then we do have to think about this. This is a vocab word that will pop up here and there. ALBEDO. That's usually a new one on folks. Albedo. How reflective an object is. And the questions on this are going to be very literally like this. I'll see if I can find one for today's classwork. I will. It's going to be what's most effective at um, absorbing energy or reflecting it. So if it's light colored and smooth, it's going to have a high albedo, therefore reflect energy. So think of a sheet of like hockey rink ice, perfectly smooth, very white. Energy is going to bounce right off of that. Whereas dark colored and rough, because rough has more surface area to be able to grab, um, we'll have a low albedo and therefore absorb energy. So an asphalt road, it's got lots of nooks and crannies to grab heat. It's dark in color, very good at absorbing energy. All right. Listen, I don't see a ton on refraction, and I know these notes are getting long, so we can do some shortcuts here. But it's basically when light waves get bent. Um, when we see sunset, it's actually already set. It's that the light waves are coming up, hooking up with our atmosphere, and then bending down in. Again, I've never seen anything more complicated than a picture of a glass of water with a straw in it, and the straw looks like it's bent. And that's what refraction is, the bending of any type of wave. All right. If you want to throw that in there, you can. I'm not going to pretend that that's one of the more important ones. It's not. Scattering. Why is the sky blue? And the answer that pops in a lot of people's head is because it reflects the lakes and oceans. And then you say, well, why are the lakes and oceans blue? This says, well, because it reflects the sky. Well, it can't be both. And the deal is that it's actually scattering that does that. The blue wavelengths, the spacing and the composition of our atmosphere are very good at scattering the blue wavelengths, like Plinko and Price is Right, if you've ever seen Price is Right, Plinko. I've used that example for years, but the blue wavelengths try to come down through the air molecules and end up getting bounced all over the place. And then at sunrise and sunset, because it's going through a longer part of the atmosphere, it's a bit more red. Again, not a huge deal on that one, to be honest with you. Okay. Absorption. And I really beat this more into you in the lab, I hope. But when the sun comes out, absorbs energy and heats up. Later, the sun cools off, which means it radiates. And that balance is going to be really important when we talk about the greenhouse effect and talk about climate change. That parking lot can't destroy energy. It takes that energy in, and then later when it cools off, it gives the energy back to the atmosphere. Like the sand and water, if you are a good absorber, if you heat up quickly, you are also a good radiator. Water is poor at both of those, which is useful. Like if you have radiant heat with like those pipes that go along the baseboards or one of those big like accordion metal things in your house, that heats up water and then just runs water through your house because water holds onto that heat pretty well. So it manages to survive, bouncing around your whole entire house. Don't worry about that part for now. So again, and this is maybe randomly in there, but this is just another example of convection. Here's a demo. I'm not going to do this here, but I've got them over there. If you're one of the people that's here and you really want to see it, we can do it. But the hot air rises when you put a candle underneath this pipe. And what that means is that the cold air gets sucked down there and you create a little convection cell in there. So, short story long, all of that. Thanks for sticking with me. Our job through meteorology is to observe how this energy transfer creates differences in the density of air. All of this was happening, the air that, if it wasn't happening, like there wouldn't be any difference in the way that the air heats, and then the air wouldn't move, and we would have the exact same weather every single day. But since air does move, and if you're sitting there saying, "Oh, what do we call when air moves?" It's simpler than you might think. What wind is. That's what gives us weather. So that's what's going to again blow this cold air into town today. You'll see some snow. If you end up doing these notes tomorrow because you're a little behind, you might be looking outside at snow. Think of what it was like today. Kind of warm, kind of rainy, kind of yucky. Thanks for sticking with me, folks. We'll talk to you soon.